שלום. איזה כיף זה להפחיד אנשים. טוב, אז ערב טוב לכולם. הגעתם לעוד מיטאפ של ביג טינגס. אנחנו נדבר על כל מיני דברים של קפקא היום, באופן מפתיע. ויציגו את עצמם גם הדוברים שלנו מפרופוינט וטיפה יציגו את החברה. מישהו מכם אגב לא מכיר את ביג טינגס? סתם אני טועה.
הגענו לפה אם לא מכירים.
לא, כי הרבה פעמים אנשים נרשמים סתם למיטאפ כי מישהו כאילו באמת שיתף ואין להם שמץ שמושג לאיפה הם מגיעים. אז מגניב.
מודים.
סבבה, הכל טוב. אז אנחנו קהילה שמתעסקת בביג דאטה, דאטה סיינס ודאב-אופס. מי שרוצה לבוא ולדבר ולהציג הרצאות שלכם, של use cases שעשיתם בחברה, או משהו שעשיתם סתם ככה בבית בשביל הכיף, אתם מוזמנים לבוא ולפנות אלינו גם בקבוצת פייסבוק, מיטאפ, אימיילים, יונות דואר, מה שזורם לכם מבחינת צורת תקשורת. ולי קוראים דמי אגב, מי שלא מכיר אותי. וניתן פה את הבמה לכפיר ולדוד, שכאן מפרופוינט, תודה רבה שאתם מארחים אותנו, גבי כאן, שעזרה ממש. וזהו, בגדול תהנו, ואחרי זה באמת תהיה לנו גם הרצאה של החבר'ה מפייבר, שיבואו וידברו על ה-use case שלהם כאן. בהצלחה.
אז קצר, רק ברוכים הבאים. ביג טינג זה פעם שנייה שאנחנו מארחים אתכם. פעם שנייה שאנחנו מארחים את ביג טינג, זה נורא כיף כי זה אחלה קהילה, אנחנו הולכים למיטאפים שלכם, לא יצאנו תודה. ומי שלא מכיר זאת אומרת קהילה מדהימה לדבר על ביג דאטה. פרופוינט ישראל, החטיבה שהיא, רוב הסייט פה, זו חטיבה שמתעסקת בקלאוד, סקיוריטי, מגינים מערכות SaaS, זה אומר Stream Processing על סקיילים גדולים, אז יש לנו הרבה עניין בטכנולוגיות האלה, אנחנו עושים את זה ביום יום, והבאנו את הארכיטקט שלנו לדבר על לא פחות מאשר אחת מהם, וכמובן שאנחנו מגייסים עובדים, כל החברים שלכם שמתעסקים בעיקר אנשי Backend, Stream Processing וכאלה, וגם תמיד ריסרצ'רים, פרודקטים והכל, אז לפנות אליי אחר כך ותהנו.
לא אמרתי סייבר.
זה קהילת ביג דאטה.
הבנתי, סבבה.
דיוויד הוא יציג את עצמו, אבל הוא הצ'יפ ארכיטקט של כל החטיבה, עוד מישהו של ישראל, כל מי שמתעסק בקלאוד סקיוריטי, אז יושבים בו עוד שני סייטים. תהנו, תודה שבאתם.
So we're doing this in English? Or
Yeah, you can do it in English.
We'll do this in English. Mostly we're going to do this in English because I can just speak loudly, it's fine. The reason we're doing it in English, by the way, beyond the fact that Demi asked, is I was looking for a translation for observability to Hebrew, and there isn't any translation. The best I could come up with is יכולת התבוננות, which sounds weird and awkward, and I don't want to keep saying that over and over. So anyway, observability is the thing. Nirut. Yeah, I guess. That's but I started in English when I say it with English, sorry. I can't switch in the middle. So anyway, we're going to talk about observability in distributed systems. As Chris said, I'm David, I'm the architect here. So we deal with a bunch of distributed systems. In general, let's do like a quick survey, right? So everyone can actually participate. Who here is working on a system which does something with more than a single service? Microservices would be the buzzword. Most people. Alright, some kind of REST web synchronous thing, services that call each other. Everybody else does more of the data processing, lots of distributed pipeline services, right? Okay, good. So I'm not going to make any distinction between those, right? Because as far as we're concerned, anything that has more than a single process is a distributed system, and the more of those you have, the harder it becomes to actually monitor and make sure the system is running as you expect. Which is really the reason for this talk. The real reason, though, is I joined Proofpoint about a year and a half ago, just a bit after Proofpoint acquired Firelayers, which was the startup that developed the core of the system I'm mostly working on. And obviously, this whole thing was developed in socket mode, which means add features and make sure the product side actually works. And forget everything else. Let's just get all the features out. Get the customers and get the exit, and then Proofpoint took over the product, and then they had to actually take this very quickly exploding product and turn it into like an enterprise scale system, scale out from about 10 customers to we're up to about 1,000 now, a year and a half later. And so obviously this doesn't come easily or cheaply, right? And so one of the big things that was really missing in the original system we started working on was the ability to actually observe what's going on internally, right? And so we spent a large part of the last year and a half actually adding tools to allow us to not just scale the system, right? Because scaling is a separate issue, but rather once we scaled all of it and added a bunch of services, how do we know the system is okay, right? And how do we know how to debug? And when things happen, how do we zoom in and actually fix them? And so that's been one of my main focus areas for the past year and a half. And this is like the origin of the talk. Right, and so before we go further, let's define observability, at least for the context of this talk, right? And so observability is, so you know how things in the industry come in waves, right? So let's say 5 or 6 years ago, everything was microservices, right? So all the conferences you went to, it was microservices, all the blogs were about microservices, blah, blah, blah. Which is not a new technology, right? Service-based architecture existed for like 20 years at least. Like the first thing I wrote 20 years ago in .NET was kind of a microservice system. So it's not new, but then most of the industry caught up, and so that was the thing 5 or 6 years ago. And then everybody started doing microservices, and then they discovered that now that you have a bunch of services, it's kind of hard to deploy all of these services. And so a couple of years later, everything was suddenly containers, because that was the solution for having a bunch of services. And so then every conference you went to, it was containers, then Kubernetes and all that stuff. And then once everybody had containers and services, suddenly they discovered that, okay, now we have a bunch of services running in a bunch of different containers, and it's really hard to debug this stuff, and we have no idea what's going on. And so, as of about 2 years ago, observability has become a big thing, right, in the industry. The industry is now catching up to the need to actually have good, solid tools to provide debuggability and observability of distributed systems, because everybody is running distributed systems now. Right, it's nothing new, but then at least most of the industry caught up, and so what was once the problem of companies like Google and Facebook is now the problem of everybody here, right? So presumably everybody here has some kind of system. So let me ask you this. Who here right now can check and be 100% certain that the system you're working on at work is okay and up and 100% working right now?
100% doesn't exist.
95%. I'll go with 95, it's fine. Who knows now with decent certainty that their system is up and totally doing what it's supposed to do?
I know 95% that it's not.
That's good. That's also a kind of observability. I noticed that there's like 15 people here from Proofpoint, not a single one raised their hand. Because you can just walk over there to the monitor and look, right? I'm just saying, there's a monitor. But anyway, okay, so that's my point, right? So we're never entirely sure the system is up, but we want to actually get to a place where we're reasonably sure of two things, right? And most questions about observability come down to two big buckets. And the two big buckets are, is anything currently wrong? And if the answer is yes, what exactly is currently wrong and why?
Which
right?
is hard.
And so pretty much every use case in observability comes down to one of these two questions. Is anything going wrong right now, or is the system healthy and okay? And if we know something's bad, we obviously want to fix it. And before we fix it, we have 20 or 50 or 500 services to choose from. How do we know exactly where the problem is? What caused it? Was it a new deploy or something systemic or something environmental? And once we know what that is, then we can go and change it, right? And so pretty much everything we're going to be talking about will be ultimately answering one of these two questions. So if you go to conferences or read blogs about observability, you'll most likely run across a version of this Venn diagram, some kind of version. And the distance between the circles usually depends on which vendor is trying to sell you something. So if you go to like an Elasticsearch meetup, the circles will be really close together and there's going to be an Elasticsearch logo in the middle. But if you read like a Datadog blog or Lightstep or one of the companies which sells metrics systems, the circles will be really far apart and their logo will be like in the area of metrics and tracing, right? And so that's why I'm not really taking this diagram seriously, but it does convey a certain point where observability is not a product you can buy, right? It's a property of a distributed system which lets you know just how well you're able to look at the internal state of the system at any given moment and make assumptions about the state or the health of the system, right? And so logs, metrics, traces, which by the way in this case, does everybody here have some kind of centralized logging system? Mm-hmm. Who does?
I have two.
Two is good. Who doesn't, but would like to? Mm-hmm. Nobody admits to. Okay. Who has some kind of centralized metrics system? When I say metrics, I mean like system metrics, CPU, and application stuff. Okay, fewer people, but still quite a few. So before I ask the same thing about tracing, in this case, I don't mean tracing in the Unix sense where you do strace and look at system calls and stuff like that. I'm talking about tracing in the modern sense of distributed tracing, where you can take a single logical transaction that starts at one end of the system, and then trace it through the entire system, find every service or everything it touched, collect all the traces and look at them as one holistic transaction, right? Which is a separate thing from logging and metrics. So who has a distributed tracing system that's actually up and running? It's
Not on everything, on 80%.
Yeah, it's good enough, right? Regardless of whether you have the system, who has a way of at least tracing the transactions? Maybe manually looking at logs, right? If you go and you actually look, all the Proofpoint guys should be raising their hands. I'm just saying. Like, okay, so my point is, none of the things are products, right? Unfortunately, a lot of the conversation around observability tends to be very vendor-driven because they're selling as products. But all of these things, logs, metrics, traces, they're just a bunch of technologies, and you can use all of them in different quantities to provide observability in areas where you don't have enough. So, for example, one of the first things we really needed when I joined Proofpoint was we didn't have enough application level metrics. Right? We had excellent system metrics, and we had some application level metrics, but we didn't really have things like, we couldn't answer questions like, is every customer currently getting events from the platform? We knew there were some events coming in, but we couldn't go and check if every customer was actually okay right now. Or we couldn't answer questions like, did we emit as many events from the service as came in? Or, for example, is our Kafka consumer lagging right now, right? So is one service consuming all the things that the other service is sending? So that was one of the main pain points we had, because a lot of the issues we had in production revolved ultimately around finding, is a certain service consuming all of the Kafka messages it's getting? And so a lot of the things we added over the last year and a half were around these areas, right? So it's not like we either have observability in the system or we don't have it. We lacked observability in certain places and we increased it, right? It's not binary. So for example, in our case, we achieve observability sort of in this area, right? So in our product, in Proofpoint Cascade, Class Access Security Broker, we invested a lot in metrics. We have very detailed system and application level metrics, and we invested a lot in our logging infrastructure. We run Elk as it happens, and so we overloaded a lot of functionality on top of logs beyond what you just normally get from logs. So for example, we do have distributed tracing in our system. We can go from one end of the system to the other and find everything, every service, a certain transaction touched, just by looking at the logs. And we actually use that to debug and to find certain things automatically. We don't have a separate distributed tracing system. We don't use any of the tools, which I will talk about later. But we have equivalent functionality over our logging system at the cost of some trade-offs, right? So for example, logging, we pay a lot more for logs, right? And we have low retention because it's just much more expensive to store a bunch of logs. But it's not that we lack the ability to trace transactions. We implemented it ourselves, which by the way I don't recommend. Right? Ultimately, if you're going to do this from scratch, obviously use a product, don't implement the same thing yourselves. But for various reasons along the way, we implemented distributed tracing on top of logs instead of actually having a product. Before we get to all of this, right? Before we can actually talk about using tools to do root cause analysis and actually figure out where the problem is coming from, we need to be able to actually know where a problem exists, right? Which brings us to service level indicator, which is a term that comes from the Google SRE book. Has anyone read the Google SRE book?
Some of it.
Some of it. Like
SRE practices.
So just so you know, and everyone, whether you do SRE, DevOps, or Dev, whatever, I think everyone should read those. Google published 2 free ebooks. Basically condensing all of their site reliability experience into 2 excellent books, which very clearly define things like how to monitor, what monitoring is about, what's observability, how to actually think about monitoring distributed systems. You don't necessarily have to implement all of it because most of us aren't running at Google scale, but the ideas are really strong, and it's really it puts a lot of things in perspective and how we should actually think about. So if you Google search Google SRE book, the first link is going to be the right link. And so service level indicators is part of what we define for a system that actually informs us about whether a service is currently healthy, right? So before we can talk about service level indicator, we need to actually define what a service expectation is, right? Which is what SLAs are for. Let's say we have a service which is the microservice which backs the graphs in our front end, right? So we have a dashboard which shows some statistics. It goes to a microservice. Microservice brings back some data, shows it in the UI. And so what's our SLA for the service? Our expectation of the service is to be available 99.99% of the time and to respond within, let's say, 1 second, right? That's our service level objective. That's what I'm saying. This defines when the service is functioning properly. And so our service level indicator would be anytime the service doesn't do what it's expected, like doesn't return within 1 second or less, or doesn't return at all, that falls outside of our service level objective, and so our indicator should actually clearly signal that this service is not healthy, so it's not performing well, right? And so that pretty much sums up of what service level indicators are. They're there to answer the first question of observability: is anything currently wrong? And so if the service is measuring outside the service level indicator range or the service level objective, we can say that this service is unhealthy. It triggered the SLI, and so one of the main things that should be very clear is that SLIs are a business level feature or a business level objective, right? Because it's one of the things the business promises its customers is a good service experience, a good user experience. If you care about user experience, you should obviously fall within your service level objectives, which you obviously need to define first before you can fall into them. And so you can define that according to whatever your business is actually doing, right? So if our business is taking events from cloud platforms, doing some heuristics, and then showing a bunch of stuff in the UI or sending alerts, so our SLIs would be things like, is the UI responsive within X seconds, and how long does it take us to process an event from end to end? Let's say if an event comes in, and ultimately we decide that this is an attack, right? And so someone has hacked the customer's account. The lower the interval of us detecting that and doing something, the better. That's our SLA to the customer. And so we can define that if it's under 10 seconds, everything is good. If it takes more than 10 seconds to detect an account breach, we're outside of our service level objective, right? So, and then we can start measuring that, and then the answer to is there anything wrong, yes or no, becomes very clear, because you can measure something, you can say, are you within this range or not? And so once you do that, you can go and you can define very straightforward indicators, right? So this is an example of a monitor which actually hangs outside over there. So on our floor, we have two sides of the floor. We have one where most of the developers are. We have the other side where most of the customer success, product, and management, our VPR, director of R&D sits there. And so this indicator hangs on the side where the product and customer success people are, because this dashboard actually shows the most important service level indicators for our system for the customers, right? It says if every column is one of the main flows in our system, so one kind of event that we process. Every row is a name of a customer, and the list actually rotates every now and then. And so these are the things we actually care about. Does a particular customer have the right level of service, right? And if it's no, it should be very clear, right? It turns red. And so you can go and you can check why that is. And then we get to the other set of questions, which is, what exactly is wrong and why, and we'll get to those in a second. But first, we need to actually have this to know if something is wrong, and we need to have a very clear signal when something is actually wrong. So I used this screenshot. I was lucky to catch it, the system, when it was actually having a bad day, because I want to talk about what is or isn't a good signal. So this actually is not something we're fully happy with, right? Nobody's ever happy with their system, and so we're not fully happy with this. One of the problems with defining SLIs is it's a moving target, right? SLIs keep updating, things change in your system, and so for this, for every customer, we defined a certain level of expectations, so for example, how many events per hour we expect that customer to have. And so for at least 3 of these customers, the red circles are false positives, right? They're not actually outside the SLI. We went and checked, and it's actually okay. We just didn't calibrate the threshold correctly. And this has been hanging on on the wall for about 2 days with a bunch of red indicators in it, which is a very bad thing, because ultimately, if you get used to seeing the circles red and you think, no, that's all right, that's fine, that's a very bad thing. It's called alert fatigue, and you don't ever want to be there. Another example would be, we have a Grafana dashboard with a bunch of monitoring alerts set up. I have a folder in my inbox called Grafana. There's 16,000 unread emails there from our Grafana. Because at this point, I just don't care. I can't read 16,000 emails, right? And so that's alert fatigue. And so if you want to define service level indicators, the main thing you want to do is you want to have very few of them, and you want them to be very strong signals, right? So another example would be, I can't show you our status page. Internally, we use status page to show automation results because we have a continuous automation running end-to-end in the system, checking different flows. It reveals way too much details about the internals of our system, so I can show it. But as it happens, Reddit, which I hope everyone knows about, also use status page for their alert system. And so they have very good, very clear service level indicators because you can't really read the lines, but it says web application, desktop application, mobile app. So all exactly the top level things customers actually care about, right? And so that's a good example of service level indicators. From here, the next thing we need to talk about is what's the difference between service level indicators and metrics, right? Because I'm sure everyone has metrics. When I say metrics, who actually thinks of things like CPU utilization and disk?
Sort of, it's a combined thing.
Right.
Of
So
that
in this case,
and the user experience things.
right. So when I say metrics, you have to have the system stuff. I'm mostly talking about application level metrics, or more commonly, it's now called APM, application performance metrics. So I'm talking about application level processes that you can actually measure and track. Okay, and so the difference between service level indicators and metrics is that, let's say, well, I can't exactly see this because there's light here, but this is our Grafana dashboard. I just took a random snapshot of the Grafana dashboard. It doesn't matter that you can see it, you won't get any of it anyway. So this is not a good service level indicator, right? Metrics are specifically there not to tell you if something is wrong, because usually, and correct me if your company is different, but as far as I know, engineers really love putting stuff in dashboards, and they have very good imaginations, and they can think of all the different scenarios where they might find something useful. So every metric you can think of exists on a dashboard somewhere. But it's a very bad service level indicator because you have way too many things on the dashboard. It's usually squiggly graphs with nothing red or green in them. And so it's very hard.
It's monotonic.
Especially that, or if it's spiky and you're not sure if its spikiness is good or bad, or if it actually doesn't matter. And so these are not good indicators. Once you have an indication of something is wrong, then the first thing you usually look at is usually metrics. You go to metrics and you try to figure out if the particular thing that the service level indicator says is wrong can be identified from your actual application metrics. And usually you can get at least a hint of what's actually wrong. So if you could see this, this is actually, again, a good example I caught about a month ago. We had a really weird anomalous usage on the website. It's because some of the data wouldn't load fast enough. And so we went and we traced a bunch of stuff, and ultimately,
Romantic.
And ultimately we found that the time it was taking events in our system to go end to end was much higher than usual, and then we traced it down to lag in rule engine. So we have a thing called the rule engine, which just reads messages from Kafka, does some heuristics on them, and then decides if this particular rule event is an account breach or not. Or I'm simplifying it very much, but it doesn't matter. And so usually it reads from Kafka pretty steadily, and so the consumption or the lag for the rule engine you would expect to be very flat, because there shouldn't be much lag. So in this case it was not lagging, but the input to the rule engine was spiking, which means the problem wasn't in the rule engine. We could trace it back to the thing before the rule engine, which is a different service, and that service does enrichment on the events before they get to the rule engine. And so it was sending events in spikes and waves, as opposed to what it should be doing is sending them flat. You guys are smiling because you know what I'm talking about. Eventually, we traced that to the fact that we were enriching events from a database. This database was, as it happens, Elasticsearch cluster, was under very high load. We traced all the requests coming into the database. At this point, we switched to actually looking at logs, because we don't have metrics about requests to Elasticsearch. We looked at access logs, and in the access logs, we found an unusual level of requests coming from one desktop computer. We traced it down. Long story short, this is why our researchers no longer have production access to our Elasticsearch. They have something better now, right? So we moved all the data to S3. They can use Athena to run queries as much as they want. But the point is, the flow of events was, we looked at the SLI and figured out that something was wrong. We looked at metrics, we figure out the general region where it was wrong, we trace it down to other metrics to zoom in on a specific component, which was a database. At that point, metrics stopped being useful, so we went to logs. We looked through logs to figure out how many requests specifically were happening, and then we could trace it down to the actual root cause of the problem. That's a very typical pattern of how you actually find problems in a distributed system, which is know that the problem exists, figure out the general region of a bunch of services around it, zoom into a specific service. At that point, you need something with more context of what's actually happening. You dig into logs, that's usually a manual process, and then you find the actual problem, right? So that brings us to logs, right? So everyone has logs. Logs is one of the probably first ways of using observability. I'm guessing, but somewhere in the prehistoric dawn of programming, there was the first Neolithic programmer banging rocks on the keyboard, and he produced the first program which said, "Hello world," and then he compiled it, and it didn't work. And so the next two lines in history were printf before hello and printf after hello to make sure that hello is actually going to work, and that's how logging was invented. And so after that, we came up with a bunch of iterations, and then eventually we figured out that logs are probably a good thing to actually read in a single place, and then Elasticsearch came along. And so let's compare logs to metrics, right? So I was talking about metrics earlier. The main benefit of metrics is they're very cheap. You can store a bunch of metrics. The reason they're very cheap is the data you're storing is actually very small. Usually the way you collect metrics is you send a bunch of individual counters over to some metric aggregator, which takes a bunch of metrics over a time unit, then aggregates them, and produces a single data item for the entire time unit. So for example, if you want to count requests per second, each request produces one datagram or one data point to the aggregator. The aggregator takes all the requests for that 1 second, combines them into one single counter, let's say 1,000 per second, and then it stores that one counter. And so it's very cheap to store 1,000 data points in a single integer, in a time series database something, right? And so you lose data fidelity, right? You no longer have the 1,000 requests, you have just one counter. But you can store a lot of them, you can store them very cheaply. So we have, I think, over 100,000 unique metrics in our system. Unique being, a combination of name of the machine, CPU, or whatever, the whole path to the metric. And it's all sitting on a single, very fat and very large machine, but just one machine. Compared to that, we have
Where are you storing that?
Sorry?
On what are you storing that?
So we use Carbon with the Whisper as the underlying data file, and Grafana on top of it. And it works okay. We switched to the new version, which is much better. So yeah. The rest of Proofpoint uses a combination of Prometheus and Kairos DB, which is something that was developed in Proofpoint, and so they keep using it. So for logs, the problem is exactly the other way around, right? You have very high data fidelity because you store every log, right? But usually, you can't store as much of it because it's very expensive. Usually you don't just store the logs, which is a problem in itself. You also want to index them and search them. And so we have a Elasticsearch log cluster of, I think, 28 machines, and the retention of like a week back. Because we log a lot, we definitely overlog, right? And even if we didn't log quite so much, it still would be very expensive compared to metrics. On the plus side, you can find individual log lines over very high fidelity and very high granularity, and that's just generally a trade-off, right? So the context you lose with requests, you can actually gain it with logs, and the combination of those gives you the holistic view of your system. Which is why for most companies, these are the two components you use to get observability. You get metrics and logs, right? Traces come a bit later when the problem becomes so complex that you don't have the solution with just metrics and logs. You have to do something slightly more complex. We'll talk about traces in just a bit because they're a big subject. So as I said, logs are expensive. You have to limit your retention. The upside is logs don't have to be just logs. You can build a lot of functionality on top of logging. So one of the first things we did when we couldn't find problems within our system efficiently, because we didn't know where the problem actually occurred. So we would know that we lost an event. So we knew an event came in from the cloud platform, or a bunch of events came in. We know they happened and they moved through the system because we can see counters, but then some of them went and got lost somewhere, and we didn't know where. Right? We knew there were fewer events at the end of it, and the metrics weren't helping us to actually zoom in on where the problem was. And so one of the first things we did was add some kind of trace ID or trace context to to the actual data item moving through the system and emit that trace ID into every log. And so this very small change let us actually preserve the context and figure out which of the different service logs actually belong to the same transaction, right? And so the distance from there to the distributed logging is actually very small. That's basically the whole point of distributed logging, where you can preserve the context of a transaction by moving it from service to service and finding something to identify every log message in the system and tie them back to a single transaction, right? And so effectively we got the equivalent of distributed tracing, obviously not as pretty, without UI, all that stuff, but the core functionality was there, and that let us actually debug very complex problems which we couldn't debug before we had that, right? We couldn't actually go and debug things like, okay, so we got the event, we enriched it, and then we applied rules to it, and none of the rules actually hit the event, and we don't know why. And so you can look at individual logs of the rule engine, or you can look at individual logs of the thing that brings in events, but you have no way to tie a specific event to a specific rule evaluation. So once we actually found a way to tie them together, we could debug problems which we couldn't before, right? And that's the essence of distributed tracing. Distributed tracing falls into this middle area between logging and metrics, where logs are very detailed but very expensive. Metrics are very inexpensive but not granular. And so distributed traces give you enough granularity and enough, and they're significantly cheaper than logs to store, for reasons we'll actually talk about in just a second. Before I switch to talking about distributed tracing, let me just go back to the point of granularity. You can always play around with granularity, right? You can always adjust just how much you're going to store. For example, right now we can aggregate metrics once per minute, and then we might discover that aggregating a whole minute of metrics is much cheaper, but not enough, because the problems we're trying to find happen at second intervals, not minute intervals, and so we can expand the aggregation we do on metrics and start storing counts per second. Obviously it's going to cost us 60 times as much, but it's much better. And even second might not be enough. As an example, not at Proofpoint, but I've seen cases where let's say logging requests at 1 second granularity was not giving enough context, because if you take 1,000 requests, which happen throughout the second, when you look at them, it's on average 1,000 requests per second. If you graph them at a millisecond level, you'll suddenly discover that most of them are bunched up at the end of the second. And so what happens is you don't get predictable latency for a second, you get nothing for a second, and then a bunch of things, a bunch of requests happening, because the garbage collection was kicking in, and so for a second the servers did nothing, and then you had a large latency spike towards the end of the second, but you couldn't discover that from just looking at the latency, because the average latency was high, but the number of requests was fine, it was 1,000 per second, right? And so the granularity wasn't there. But then if you go and you look at the logs, you can see that each request actually takes a long time. And so that brings us back to tracing. So as I said, distributed tracing, in a very small nutshell, is the ability to take the context of a particular request and propagate it through every service the request touches, and then in every service take the identification of that request and emit it into a log. And so effectively you have two communication channels. One is inline, so you have a very small piece of data which is moving through your system. So if you're using web requests, you put it in the web request as some kind of metadata on the request. If you're doing some kind of message passing, you attach it as some kind of header or context to the message. So in our case, because we have to support an ancient version of Kafka, which predates message headers. So by the way, for those who don't know, Kafka supports message headers, just like HTTP. Very few people know this for some reason. We know this, but we can't use it because we have an older version. And so what we do is we actually put the actual request ID into the data itself. We mostly use Kafka, and so the Kafka message itself contains the transaction context ID, whatever we call it, I can't remember the actual name, which gets generated at the edge of the system where the data first enters and persists through everywhere, and everything that actually puts out logs writes the transaction ID into the log. And so if I know that a particular transaction happened and there was a problem with it, I can go and look at the first service in our system, find the request, can take the transaction ID, search for it in Elasticsearch, and I'll find every single thing that the transaction ever touched. Right? And that's basically the idea of a distributed system, except you don't overload it on top of a logging system. you actually use a separate system to emit traces outside of the process. And so inline, you have very small data moving through the system, and out of line, right, you emit much larger traces with full context, which sounds very much like logging, right? It sounds pretty much exactly like logging. And so the question is, how is it different from logs? Usually, most implementation of distributed tracing are not interested in full granularity detailed logs. They're interested in statistical sampling. And so one of the things normally distributed systems do, distributed trace systems do, is sample the traces. You don't log every single trace request, you log every request out of 1,000 or 10,000. So one of the first distributed systems ever built was a system called Dapper at Google. They pioneered a lot of the technology around tracing in general, or just in general. And so in Google, Dapper did pretty much this. They had a very small context passing from request to request, and they emitted traces, and they sampled 1 out of every 10,000 requests. Because at their scales, even having 1 out of every 10,000 samples was much more data than they actually needed to measure and trace end-to-end latencies and find problems, right? And so there's two things you actually have to pass through your system to preserve the context. One obviously is the transaction ID, and the other, which helps a lot if your system is dynamic and data can take different paths through the system, you want to know which service preceded the one you're in right now. So we have services, let's say A, B, and C, and service A calls service B over HTTP, and service B sends a Kafka message to service C. Right? Service A would generate a transaction ID, and it would send the transaction ID plus its own name or some kind of identifier saying I'm service C over to service B, right? Or service A over to service B. Service B would take that, remove the service A name, put itself in that, and send that downstream to service C, right? And so every service knows where the request came from and what the request context is. Once you emit that into the logs, you can reconstruct the entire graph of everything in the system that transaction touched, right? And so if you want to go and map it on a graph, and we'll actually look at a few examples of how you can represent distributed traces in the UI, you can actually see the latency waterfall graph over all of the system, right? And so generally, if you look at this, most distributed systems define a concept called spans. So a span is the logical unit of work between two, that's interesting to measure. So for example, if it's a REST request call, a span is the entire request. Or if you're doing Kafka, so a span would be from the moment you produce a message to the moment another service consumes the message. That's an interesting span to measure. And so a typical request might look like this, right? You have one service calling another, and so you have an overall span A, which encapsulates a bunch of internal requests, synchronous requests. It called span B called span C, and then D sequentially, came back and then called span E. And then that thing produced a Kafka message, which isn't synchronously tied to the previous span, but it follows the span, right? And so distributed tracing defines two kinds of relationships between different spans, which is child of, which means the child span synchronously, the parent span depends on the child span synchronously, and follows from, which is two spans are related because they're part of the same transaction, but they're not synchronous, right? They don't actually belong to each other, they just follow each other chronologically. And so this actually is the span diagram of the previous request example, where one service calls another and then sends a message to a third one. So once we have this, once we capture all this trace information, let's say we do some kind of sampling, we store 1 out of every 100 transactions, right? And this, the strategy of actually sampling can be very, very complex, but let's say we just randomly take every 1,000th transaction, or 100th transaction. Once we do that, we can answer questions we couldn't answer before. So we can answer primarily business-oriented questions, like, am I within a particular SLA? I can look at end-to-end transaction and measure latency, not just between two services or between two known edges. I can actually look at the entire graph and find which specific service is responsible for an increase in latency. If we can tie this back to something like a CI/CD system, we can go and tie this change back to a particular deployment and say, okay, this deployment changed the latency in this area of the graph. And once you actually graph this, visually, you can actually represent the state of your system much better and use this for root cause analysis. I'm going to skip a few because Demi keeps signaling me with like fingers, which I'm guessing means you should move on. I don't know what that was, but that was a middle finger.
One of them was.
One of them was the middle finger. That's the one I was looking at.
You can do this, but it's the same.
So I'm going to skip to a few things and then get to the actual interesting point, which is distributed tracing is relatively new, and so it's not well established. There's no one basically standard for things that we have, like in things in logging. So if you want to do logging, you know there's log4j, you add it to your application, or there's log4net, you add it to your application, and logging is done, right? So open tracing is not at that level of standardization yet. There is a project called Open Tracing, which attempts to do for tracing what log4j basically did for logging, which is you bring in a single dependency, you instrument your application in a few places to emit traces, and you're done. And so open tracing emits traces in a standard format, and then every system which supports tracing can have a collector that supports that format, and you can collect traces from all of your system. And if you want to swap which database you use or data store you use for traces, you can do that transparently. If you want to change the implementation of the actual trace output collector, you can do that because your application uses a generic API to emit traces, right? So there's a whole world of content that hides behind just the name Open Tracing, so you should go and you can actually read about this. It's very interesting. I'm going to skip a couple more because I want to actually get to the tools you should actually look at. So there's a whole bunch of tools which support distributed tracing, where you can emit a bunch of data from a bunch of services and then visualize it. Generally, they fall into two categories: managed services, and if you have the money and the expertise to use online services, I strongly recommend using those first. It's much easier to integrate. I'll actually move a bit. So managed services obviously cost money, but they're very good, and they usually, on top of just storing traces and giving you statistics, they usually have a lot of intelligence and alerting functionality that you can actually reuse. So Datadog and Lightstep are like the top of the list. Every cloud platform has something like this. So Amazon has X-Ray. The main problem with X-Ray is that it's very Amazon-ish, which means it supports none of the standards at all. It doesn't support open tracing. You have to write your own. It's very good, has nice UI, but if you want to be able to to move to a different vendor, tough luck. And then the other part is the self-hosted projects. Almost all of them, except the last two, are open source. Elastic is part of it is open source, part of it is for pay, and it's actually brand new. But pretty much all of them can collect traces from an open tracing implementation and then graph them in some way, right? And in the minute and a half that one finger Demi was showing me, we'll look at a couple of UI examples of how this actually works. In most of the tools, you'll find something similar to this, which looks very much like the network diagram you get in a web browser. It looks at a single request and then breaks down the request into chunks and measures latency for them. And you can go and actually see, obviously it's not a single request. You can look at one request, you can look at the average request latency across your system. That's more interesting. This is, that's Elastic APM. Yeah, that's Kibana. I'll go through a few of them, right? But they mostly look very similar. So this is actually backed by Elasticsearch. Most of these open source tools ultimately use Elasticsearch under the hood to index traces. The difference is, unlike logs, they don't index every trace, they index very few of them. This is Jaeger, which is an open source tool. It also has the same waterfall diagram, but it has a very cool feature I like, where you can take two snapshots of traces and compare them. Like you would do, for example, CPU sampling. You can take a couple of traces, one for 5 minutes yesterday and one for 5 minutes today, and see if at the service level anything changed, which I think is a really cool feature, and it's actually very nice for investigating where latency increased or where some kind of load actually increased. We can look at Zipkin. Zipkin is another open source tool. Again, looks very similar. The screenshot is from the Confluent example. They're a very cool example of using Kafka streams with Zipkin, which you can just download and run and play around with. You can't see this one, but it's Apache Skywalking, another example. And this is AWS X-Ray, which I wouldn't personally use, again, for the reasons I said, because it's very not standard. But on the other hand, they have really cool UI, so that's one of the things they have, where you can actually look at all the dependencies in your system and look at the input and output latencies across them and actually define CloudWatch alerts on increases in latencies, which as a feature is really cool. And so there are a few tools which do something very similar. So just in conclusion, right, when we talk about observability, it's not a thing we have. It's not a product we can buy. We want to focus on areas where we lack observability, which is something you can actually measure. You can figure out where you're spending most of your time debugging and what's hard to debug, and then try and increase observability there. From experience, what we learned at Proofpoint over the last year and a half is that it pays to be brave and not try and add observability at the edges of your system, because that doesn't actually produce very good value for your effort. It pays to actually go in, find the area that's actually most painful, do a bunch of work there, and then you get a lot of results, right? So if you're gonna do open tracing, don't find the least important service that's least critical in your system and add traces there. Find the most important 3 services in your system, instrument them for tracing, and then figure out if that's actually giving you value, because you're going to see something much more valuable right away. Same thing if you don't have metrics or logging, but you should have logging, obviously, and you should also have metrics. And before you can do any of that useful stuff, you really have to rethink how you define SLIs. And one of the ways you sell this observability stuff to product and business and support and everybody is to understand that this is a customer level feature, right? Observability is as much a feature of a system as a nice UI or a good whatever the thing you're selling is, right? Because having observability lets you actually get to the customer experience and sell a better service to a customer. And so if you're going to talk about should we invest time in doing centralized logging or doing distributed tracing, the reason you should do that is because yes, it's a major feature of your product. And that's it. Thank you very much. If you want questions, I'll be over there with the beer.